All right. That awing you hear is in the background is because I said this might be our last one ever, last lecture ever. All right. So where we left off, we found the potential for a reaction. Now we have to find overall potential for a different reaction. So your first step is to figure out what is being oxidized and what is being reduced. So we count I2. Oxidation number is 0. Al, oxidation number is 0. We have an ion. So what's the oxidation number of an ion? The charge. And here we go. I minus is just minus. So look on your sheet, your reduction potential sheet. That's a good thing to have out while you're watching these lectures doing the problem set. Problem set 21 is now available. It's at the door. For those of you listening at home, not your door. It's at the door of the school. I did not deliver them to your door. Okay, so yeah, delivering to the door of your room, not professional, just creepy. All right. So what is being oxidized? Which one is losing electrons? Al is losing electrons. I2 is gaining electrons. Okay, so we look. If I2 is being reduced, we can look exactly on our sheet and find the reaction. So we look, I2 plus 2E minus makes 2I minus. And the E naught value is what? 0.53. All right. Now, when you are oxidizing something, you flip the reaction the other way. So it's not your reduction reaction, it's the oxidation reaction, which is the other way. So in this case, it's Al3 plus makes Als plus 3E minus. What is the E naught for this? Right, so it's 1.66. On your chart, the flipped version of that is negative 1.66. So here, when we flip the reaction, the sign changes. So it goes from minus 1.66 to 1.66. So we now have a 2.19 volt E naught for this whole reaction. Very favorable. Very favorable. So we're going to get to it on the next slide. All right. Now, you could say, Mr. Bennett, but wait. What did you not take into account? I did not take into account the coefficients. Oh. It's 3I2 and 2 ALs. You ignore coefficients. You don't multiply by anything. This is the one time where you ignore the coefficients. So you might think, oh, I should have 3 times 0.53 and 2 times 1.66 to get my E naught. You just look at the individual half reactions, regardless of the coefficients. Where we will start worrying about the coefficients is when we start counting electrons. Okay, so I started with, the question was, why are the 3 electrons on the right-hand side? So I start with solid aluminum. And then in order for it to go from solid aluminum to aluminum 3 plus, what has to happen? Oh, yeah, no, you're right. It should be switched. So, but why do I not have? Oh, that's why. I screwed. Here's where I made the mistake. I didn't switch it. I didn't flip it around. Thank you. Flip. So, really, what you're doing is this. Thank you, Elena. Wait, 3 plus. Where am I? Just ignore this one. You just accept, I'm asking you to accept for the time being that the coefficients are unimportant for the time being. All right. So we're off to a rocky start, but we're gonna unrocky start it. We're gonna smooth out the road. There is a slide missing here, which is interesting. I say that we're off to a rocky start and it's going to get better, and then of course there's a slide missing. All right. Your next slide should be. Do you guys have a next slide that's? Yeah. All right. All right. All right. So, your next slide should be this. You should have this. Now, we're going to try to loop this back to thermo. The equation that connects these two. Who remembers our equation for gravitational potential energy? Let's do on Earth. MGH, like the hospital. All right. So it looks like MGH. We have delta G naught equals negative N fancy F. I can't do it, but it's a fancy F times E naught. Now, what do these things mean? Well, we know delta G is our Gibbs free energy. So this is an F. It's a fancy F. I don't know why it's a fancy F. It's just a fancy F. Negative N. And what do we know? What is N? Number of moles. Now, it's the number of moles of electrons transferred. So in that last equation, we would look at the coefficients and see that in my balanced chemical equation, I had transferred 6 electrons, 6 moles of electrons, right? That's where you need the coefficients. To find your E naught, you don't need it. To check your free energy, you do need it. F is Faraday's constant. The comment was, you saw it in a Simpsons episode. What have the Simpsons not done? All right. Yes. Okay, this is Faraday's constant, which is 96,459 coulombs per mole. What does coulombs measure? Charge. Charge. All right. E naught is the cell potential in volts. So if you have your E naught value and you have the number of moles transferred, you can find the Gibbs free energy for a cell, for a redox reaction. Now, we're not going to go into this much. What do we care about? We care about picking a color. Green. So, if E naught is greater than 0, what does that mean delta G has to be? G naught is less than 0, so it's thermodynamically favorable. So the question was, it doesn't want, or the statement was, it doesn't want to have higher potential. That E naught measures the potential of the reaction happening. Like, what is the driving force? So we think about in a circuit, we think of volts as the push. So if we have positive voltage, we can push the electrons through, right? Which makes it spontaneous. Or, sorry, we're using thermodynamically favorable, right? So the key takeaway from this slide is this. If your E naught is greater than 0, your delta G is less than 0. Therefore, you have a reaction that's thermodynamically favorable. So we've now linked together electrochemistry and thermodynamics in one neat little equation. So the question is that because current flows opposite to electrons? I hate Benjamin Franklin. I said it. There, I said it. Why do I hate Benjamin Franklin? Because Benjamin Franklin is credited with he didn't discover electricity. He defined electricity. Like, electricity was always there. It's not like he invented it, right? He just was the one who sort of explained it first. Well, so when he started explaining electricity and talking about current, he had current moving. Well, what did they not know about in 1787 or whatever? Everything. Come on, my freshman physics class knew this today. What did they not know about in 1787 that would be important for electricity? The electrons, thank you. Electrons. So they did not know electricity was the flow of electrons. So when Benjamin Franklin started describing things like current, he didn't know about electrons, and he didn't know that it was the flow of electrons. So now current is, there's a distraction. Current, we actually describe current as not the flow of electrons. It's opposed to the flow of electrons. It's like the absence of electrons, like gaps. It goes opposite to what you would expect. Current flows from positive to negative.
So is that why there has to be a negative vector?
This is not why there has to. The question was, is that why it has to be negative? No, this just has to do with the connection between free energy and E naught. But the flow of electrons is not the direction of your current. It's opposed to the direction of your current.
Because I mean, if current goes the other way,
No, not necessarily. We have the positive and negative, so it's still okay. So that was just my little rant about Benjamin Franklin and. Okay, interpreting the E naught table. You have something that looks like this. So, what do we know about fluorine? Well, fluorine, highly electronegative. Most electronegative element there is. This wants electrons, right? Fluorine really wants electrons. So what do you think that means about the reaction of F2 plus 2E minus making 2F minus in terms of favorability? Very favorable. Very happy. So equals favorable. Now we get down to lithium. Lithium does not want to gain an electron. Let's go back to our fundamentals for a minute. Lithium. Why does lithium not want the electron? Doesn't have an octet. So lithium, if the lithium ion were to gain an electron, where would it go? It would go into the next energy level, right? So, which is much further away from the nucleus. So lithium gaining an electron, much further away. This is energetically unfavorable. So this is no. This is no. We're just going to say this is no. This is unfavorable. So the reduction of lithium is the most unfavorable reaction you can have in terms of reduction. This has the lowest reduction potential, which means it's the least favorable of all the things on the table. So the way I just like to write an arrow, increasing favorability. So the question is, are noble gases counted in all of this? No. I'm not quite sure why. I mean, you just wouldn't do it. You wouldn't. They couldn't. Noble gases wouldn't gain an electron. They can be excited, but you could have solid lithium. So you can flip the lithium around and look at the oxidation of lithium, which is extremely favorable, right? And so lithium, the oxidation of lithium, extremely favorable. Where do we hear the word lithium before, or frequently? Batteries. Batteries. We hear lithium in batteries. It's extremely, extremely favorable oxidation. right? So as we're talking about electrochemistry, so it makes sense that lithium would be in batteries because it's so favorable in oxidation and unfavorable in reduction. All right. Now, why do we care? I mean, cell potential and that is, oh my God. Well, see previous slide. Dun dun dun. Wah, wah, wah. All right. So I'm not going to show you this, but I'll post this. If we want, which we do, we can separate these two half reactions into things called cells. And not the cells in your body, but electrochemical cells. And we can use that to make electrons do work for us, like running a motor, light bulb, your cell phone, anything. So we can make batteries by separating the oxidation reduction reactions and making the electrons travel through a wire and doing work. Okay. So I do recommend watching these. They're pretty neat. It just shows you visually what's happening. But here is a galvanic and / voltaic cell. I used to know the story of why it's called both. I've forgotten it over time. I think it has to do with like both people discovering it independently and like Volta taking credit for it, and I don't know. There's some interesting story that I no longer remember. But here's what you need to do. You need to be able to look at a situation like this and say, okay, what the heck is happening? We have two cells. This is like, you can think of this as like a beaker. This is like a beaker. And in this beaker, you have a solution of Zn2+, and you have a stick of solid zinc. This is connected to a wire, and this wire is connected to a stick of copper, which is sitting in a solution of copper ions. Also connecting them is a salt bridge. Now, in order for electrons to flow, what do you need? Oh, that's a terrible question. How should I ask this? So, if I took this off, would electrons be able to flow? Why not? If I took the salt bridge away, would electrons be able to flow? Charge would build in one cell. So what do I need? What do I need to do? There's a C word. Have a complete circuit. You need a complete circuit, right? You need a complete circuit for let's go back to our freshman physics. You need a complete circuit for electrons to flow. Aqueous. Thank you. Yeah, like a solid. It's not a. Oh, I'll explain in a minute. So you don't want a brick of salt. It's not like you're feeding deer. Like, yeah, I was like a salt lick. No. So you want this is like a porous membrane that I'll describe in a little bit more detail later. Okay, so we look at what's our overall reaction. Well, we have two half reactions. We have Zn plus 2e, Zn 2 plus 2e minus makes solid zinc. And we have Cu2 plus 2e minus makes CuS. Now, what I want you to do, look up the reduction potentials. I think we might have done this already. But look up the reduction potentials for each of these reactions. Okay, so tell me, what is the zinc E naught? 0.76 volts. And what is the Cu? Be careful, there are two Cus. Okay, now, this is not thermodynamically favorable. We have to flip one of the reactions. Which one are we going to flip? We're going to flip this one. Which makes this positive, which makes this 1.1 volts. Okay, so now I know what's happening. Solid zinc is giving away 2 electrons and making the zinc ion. Copper is gaining 2 electrons and making solid copper. So what is going to happen visually? So I have solid zinc going to the zinc ion. What's going to happen over here? So one thing that's going to happen is electrons are going to move this way. Right? But what else is going to happen? Solid is going to dissolve. Solid erodes. So if the solid is eroding, what's happening to this? The concentration of Zn2+. Concentration goes up. Okay. Now let's walk over to copper. Copper is gaining 2 electrons, so what's happening to this? It's expanding. It's getting bigger. It's growing. Solid added. And what's happening to the concentration inside? It's going down. All right. Now, here's the weird part. If my concentration of 2+ is going up here, my concentration of 2+ is going down on the other side, that means there's an imbalance of charge. So in this aqueous salt bridge, you can use things like KCl. Cl is going to flow this way. The anion will flow out to equalize the charge, neutralize the charge. And here, the K+, the cation, will flow out to neutralize the charge there. So the question is, I'm not understanding what a salt bridge really is. That's fair. So imagine this is just like, so it can take many different forms. A lot of times you'll actually see it as just like a disc in between 2 like beakers. Like you have special beakers that have like a thing that has a disc in between. So think of it almost as like a cotton ball soaked in KCl. So like this whole thing would be filled with a mesh. That mesh can have KCl in it, and that allows for the ions to flow back and forth to equilibrate. Well, charges always want to neutralize, right? So if you have a positive buildup here, or sorry, negative buildup here, then that potential energy for that is high. So you want to lower that potential energy by adding positive ion. So the question is this not a negative buildup? Is it less positive? Well, in order to have the Cu2+, you also need, there's probably also going to be a bunch of anions in here, there's also going to be anions in here as well. Right? You can't just have a solution of positive stuff. It needs to be neutral, electrically neutral. So you would dissolve CuNO3 or CuSO4 or something in there. Yeah. So the question is, why are we just able to flip the equations as desired? So it's not that reactions are reversible, right? So you can look at a reaction as going either way. If we look at the thermodynamic favorability, it's only going to work in one direction. So the question is, the statement is you pick what direction you want. No, you don't get to decide. You look at the possibilities, and you flip it to make your E naught positive. You're looking for the favorability. You're looking what's going to push your reaction forward, what's going to make the reaction happen. And the only way the reaction will happen is if you have a positive E naught. You're not flipping the reaction. You're just right. So you're not physically changing the reaction. You just know information about these two half reactions, and so you're seeing which way it's going to work out. Okay, so what you need to know, other than the basics of this, is what is happening here? Is zinc being oxidized or reduced? Leo occurs at what we call the anode. Occurs at the cathode. There's something about red cat, red cat and an ox. Like, Yeah, there's a saying that I can't remember. Like, reduction is red cat. I have a red cat, like Clifford, the big red cat. And Paul Bunyan and his ox. So, like, anode is oxidation. Just a way to remember it. So oxidation happens at the anode. Clifford happens at the cathode. Yeah. All right, well, whatever. I don't know. I should know this, shouldn't I? He's a big red dog. All right. Yeah. No, don't do opposites. Don't do opposites. You'll get mixed up. All right. So just here, guys. There are mnemonics for this. It's the red cat and ox, but anode oxidation. Just remember that oxidation occurs at the anode, reduction occurs at the cathode. Okay. If you have to label it. Yeah, Dominic. Yeah. We're going back to the salt bridge. Yeah. Something like that. So the question is, what makes the anion go to the left and the cation go to the left? Yeah. Oh, so it'll just diffuse. The question is, what makes it get? It'll just diffuse through. There's a potential, like if you guys, I'm not sure this is perfect, but if you've done electrophoresis and AP Bio, like it moves based on electrical potential. So here, we have a buildup of positive charge, so the negative is going to want to move towards it because it's attracted. Right. All right. So here's what one looks like more beautifully done out. This is exactly what we just diagrammed, right? Here's our salt bridge, KCl. We have a voltmeter so we can measure the voltage. If we put a voltmeter here, theoretically, what should this voltage across this wire measure? 1.1 volts, right? It should be whatever our cell potential is. There we go, right? So we have the migration of ions, and we have a complete circuit, so we can get the flow of electrons, and we can make those electrons do work for us. So I want you to predict now. I want you to be able to look what's going to happen here. So here's what you do. You look at your standard reduction potentials. You look at your half reactions. You decide from these half reactions which is oxidation and which is reduction, and then tell me what's going to happen. Canary cardstock, because that's what happened to be in the copier at the time. And it's only one page. All right, figure out your half reactions. Guys, you can only flip one. You can only flip one. And you want it to be as positive as possible. So you can always find a way to make it positive. Doesn't matter. Yes, there's all kinds of different batteries, right? Yeah. This is like back in the day batteries. Now we have much fancier ones. Okay.
Oh, I have a way to remember how to
What is it?
cut out
Sort of, but then I want more like visualization of electron flow.
It's like cut out cells losing electrons, and so is oxidation.
Oh, stop it. Oh, I thought you were critiquing my handwriting. I have 0.23.
Oh yeah, sigma naught.
Oh, okay. So guys, what you might find is that your sheets might vary by 200ths. You know, you might have. I found 2.3. You guys say it's 2.5. Luckily, my 3s and 5s look somewhat similar, so it's easy just to switch. It's negative 0.25. Okay, so that's way off. Now, how am I going to flip this in order to make it thermodynamically favorable? You flip the aluminum. Aluminum, guys, is almost always going to be flipped. It's almost always oxidized. It's very easy to oxidize aluminum. And we're going to get to that. That's actually one of the slides further up. Okay, so let's rewrite this. Okay, did I do my math right? So, let's go back now. Let's say which one is being reduced and which is being oxidized. All right, so let's go back. Al, oxidized. Ni is being reduced. What does that mean? What side is this? What do we say that is? Anode, it's an ox. And this is Clifford, the big red cat dog. We don't have Clifford books at home. All right. So, now visually, guys, what will you actually see happen? If this is the anode, what are you going to see happen here? So, well, hold on. We'll go through. Yeah, a little bit. Well, we'll get to the battery side. All right. All right. All right. This side grows. Electrons flow which way? Guys, shh. Which way do electrons flow? Electrons flow this way. And so we're going to have anions flow down here, and cations flow down here. Of course, you won't be able to see this. All you'll be able to see is the aluminum eroding and the nickel growing in size. The question is, why does it matter where they go? I just want you to fully understand what's happening. All right. Now, let us go back to our delta G and our delta G naught. Did I... Hold on one second. I might have missed an important point. Oh, what's the most important thing about standard conditions? 1 molar. Okay. That was the connection I wanted to make. Now, as this is happening, what's happening to my concentration of Al3+? Concentration is going up. Concentration is going down on one side and the other. Are we at standard conditions anymore? No. So, as this is happening, delta G moves to 0. I start with delta G naught as being less than 0 because it's thermodynamically favorable. As the reaction proceeds, my concentrations inside the cells change. As the concentrations inside the cell change, delta G moves to 0. When delta G equals 0, what do we know is happening? it moves towards equilibrium. And at some point, this year, guys, be happy because there's an equation, the Nernst equation, that allows you to solve for all kinds of different parts, like when will we reach equilibrium, what's your voltage after, if we have different concentrations. You only need to understand it qualitatively. As this concentration of Al3+ goes up and my concentration of nickel 2- goes down, my driving force for the reaction is less. That reaction is less favorable as my concentrations are changing. So as it becomes less favorable, my delta G approaches 0. So the question was, and a very good one, is that why if you had a light attached to a battery, it will dim out instead of just going out all at once? That is why. You have your voltage. Well, if you put a meter in here and just let this run and let this run, let this run, your voltage would continue to decrease. So your brightness of your light would go down. So batteries don't die. The voltages start to drop. When we say batteries are dead, it's just under the threshold of what we can use. And so the question was, do batteries just have a lot of this? They just have a much more efficient way of doing this. How do you recharge a battery? We're going to get there. Yes, we're going to talk about recharging batteries. Okay. So, are these reactions not spontaneous? Thermodynamically favorable. All right, so now, figure this out instead of drawing circles. Figure this out. Are these reactions thermodynamically favorable? It's fine. I just give you a hard time. Now, you need to figure out what are the two half reactions that are occurring. You need to look at your E naughts, and then you figure out if it's thermodynamically favorable. So look at your sheet. Find the two half reactions. Now this one is, you cannot flip this, guys. These you cannot flip. These are given to you. It's showing an arrow in one direction. You are always ignoring the coefficients when you're finding E naught. You are always ignoring the coefficients. We'll get there. So I'm giving you hints as to what the reactions are. We're not going to finish today. You guys won't get the last part, unfortunately. Yeah. Yeah. Okay, so I'm happy people are diligently working away. Now, let's look. Magnesium, what is the E naught for magnesium? 2.37. Wait, is this being oxidized or reduced? It's being oxidized, so what is the E naught? It's not negative, it's positive. I know you told me positive, but I'm just saying, if you look on the sheet, it's negative, right? So we flipped it, it's positive. This is negative 1.66. So we get math. So is this thermodynamically favorable? Yay, it's positive, thermodynamically favorable. Silver, negative 0.80. Copper, positive 0.34 in this direction. Negative 0.46 volts. That is an ugly 46. Negative, sad, not going to happen. All right. So this would occur if you only allowed electrons to flow in one direction. This reaction would not proceed. The bottom reaction would not proceed. The top one would. So the question is, you cannot change the voltage you get. You can by changing the concentrations of the materials to go to non-standard conditions. And you can choose your materials to get the voltage you want. Yeah? Mm-hmm. So the question was about the values. Whenever it's oxidized, you just flip the sign. So you see how you have a bunch on that list that are positive and a bunch that are negative? So if it's oxidizing, you flip the sign the other direction because it's the opposite reaction. There's no hard and fast rule about if it's oxidized, positive, reduced, negative. Nope. You have to look at that chart and know that's reduction. So if you oxidize it, you flip it. Okay, effective concentration. Now, E naughts are measured at what concentration? E naughts are at 1 molar. What if concentration is not 1 molar? So here's what you do. Use Le Chatelier's principle. Le Chatelier. Le Chatelier. Le Chat. All right. Now, what do I mean by this? Let's look at this reaction. Oh no! I have 0.001 molar manganese, 3.0 molar tin. So, find the E naught for, assuming this was 1 molar on both sides. Find the E naught for this cell, please. I will go back to the last slide as others are looking for E naught. For tin and manganese. We are not using the Nernst equation. We are going to predict. We're just qualitatively. Yeah. Yes. Mm-hmm. We used to do that, actually. Last year's slides. We don't need it this year. Okay. So, as you guys are doing this, I'm going to also write it down. But I want you guys to practice figuring this out. Okay. Do people agree with me that the E naught is 1.04? Or did we not get there yet? So tin, I might be wrong. I looked at these. I don't have my E naught sheet in front of me. So let's look. Guys, manganese on our sheet. Is this being oxidized or reduced here? Oxidized, so we flip the number on the sheet. Is it 1.18 when I flip it? Tin is being reduced, so we just take it directly from the sheet. On the sheet, is it negative 0.14? Okay, so we get 1.04. Now, in order to determine what will happen, we need to write out the entire equation. You know what, I'm going to do it down here. Now, the electrons, I'm just going to leave out because they're the same on both sides. All right. All right, so now we have our net ionic equation that describes what's happening. Solid manganese plus tin ion makes solid tin plus the manganese ion. Well, let's look at our concentrations. I have a very low concentration of manganese ion and a very high concentration of the tin ion. So we use Le Chatelier. We use that equilibrium principle. Give me a color. I heard purple first. So which side, if I have a lot of the tin, if I'm above my standard conditions, which side gets pushed up? So if my tin is at a higher concentration, which way will that push the reaction? So if I push my reaction to the products, what do you think that means about my voltage? My voltage increases. Yeah, Michael. All right. So if my reaction is shifting to the products, if I'm making more products, I have more of a driving force for the reaction. More driving force means higher voltage. Now, mangan and ox. Yes, this is the anode. And this is the cathode. No. But so the guys, listen. This concentrate, we haven't talked about this side yet. All we're doing is talking about this side right now. The tin is high. So that means there's a lot of it in solution, which means the driving force for it to be solid is going to be higher. Now, my manganese is low. This went down. Which way does that push my reaction from Le Chatelier? Also pushes it this way. So both of these things push towards the products, which tell me that I'm going to have a higher voltage than my E naught. Yes, there is an exact way, bless you, of finding how much greater E is than E naught. You don't need to know it. That is something they took off the AP exam this year. That's the Nernst equation. Yeah, it was last year. It was on it. So look at, guys, in order to figure out if your E is going to be bigger than your E naught or smaller, take your net ionic equation, use Le Chatelier. If it pushes to the products, your E is greater. If it pushes back towards the reactants, your E is smaller. Okay. Can I move on? We have 15 minutes. Power through. I saw an oh my God in the back. I don't blame you. I feel the same way. All right. So if Le Chatelier says your reaction moves toward the products, your voltage is going to be greater than your standard voltage. If it moves back to the reactants, it's going to be smaller. All right. Now, it turns out that you can have the same reaction or same materials at both your anode and your cathode. These are concentration cells. I know, mine's just blue. All right. So this is electricity. Maybe. Electricity based only on change in concentration. So see, I have silver in both of these. Now it turns out, if I have different concentrations, we'll have a different driving force for the reaction. So, if I compare these two, I have 5 molar silver ion and 0.0015, or 0.00001, or 1 times 10 to the minus fifth molar silver on this side. Which side wants more ions? This side wants ions. This side wants less ions. If I merged these together, right? If there was a membrane between the two that allowed ions to flow, they would move from here to here, from right to left. But I separated them. So now I have these two different concentrations. And I have silver in both of them. So, if you think about it, one of them, the one that wants ions, is going to do this. And the one that doesn't want ions is going to do this. So these two reactions are going to happen. Is this oxidation or reduction? I'm hammering this home. Oxidation. So this is the anode, and this is the cathode. So this is my anode, and this is my cathode. Now, in previous years, again, we would calculate the voltage from this. Well, what is my E naught for this reaction? By definition, 0. It has to be. We have the E naught for this, which is some number. We have the opposite for this, which is the negative of that number. So my E naught equals 0. But due to these changes in concentration, I can get electrons to flow along the wire. E minus will flow along the wire. All right, let's see if we can get through like... Okay. Am I good to move? Yeah, Julia. Yep. Yep. Yeah, that's what's going to happen here. So at the anode, oh wait, did I flip these? No, I flipped them. Thank you. I had them, I flipped the equations on my notes packet without flipping the anode and cathode. So thank you for paying attention. I was just testing. Right. Well, it's the end of a day. It looks really nice out. So I'll say this, guys. Like 2 years ago, at this time of the year, it was like 70 and 80. Lecturing those days was brutal because nobody wanted to be here. Everybody wanted to be frolicking outside and enjoying their youth. But which I can't blame you for that. All right. So if a redox reaction is not thermodynamically favorable, we can force it to occur by applying an external source of electrical potential energy. This is when E naught is less than 0. So delta G is greater than 0. This was on your test. No, exactly. This was exactly on your test. Your last test 2 of term 3. We asked you about water. We asked you about the electrolysis of water. I believe it was the electrolysis of water. And we asked you why you had to apply a current to it to get the reaction to happen. Right. So there was an unfavorable reaction. You can couple an unfavorable reaction to energy to make it occur. That was the answer we were looking for. If you have an unfavorable reaction, apply a source of potential energy, you can make unfavorable reactions happen. And that's what we can do with electrolysis. So on the test, it was something like, I think it was the electrolysis of water. What's that? The problem with the electric current. Yep. Yep. And so we were expecting you to say, now, some of you got full credit. Because if you had delta G being negative, and you did not observe a reaction happening, what is the only thing that applying energy will help you do? If you have a favorable reaction that you don't see happening, what is applying energy going to help you do? Overcome the activation energy, right? So if a favorable reaction is not occurring, the only reason it's not occurring is because the activation energy is too high, right? Kinetics versus thermodynamics. Okay. So this is what we use to recharge our batteries. So we have this bridge where electrons want to flow this way. But when we take our cell phones, plug them into the wall, really what we're doing is we're taking, so if we have an E naught, I forget what the E naught of this is. I know we did it. It's back in my notes. My E naught is 1.10 volts moving this way. So my E naught the other way is negative 1.00. Now, all I need to do to make electrons flow the other way is apply a voltage greater than 1.1 volts to this cell. So, hold on. Apply voltage to move E minus back. Just like there's a positive and negative end of batteries, there's a you can apply the voltage in a way that makes the. So I'm not sure exactly why you can overcharge your phone, but eventually you use your charge, you plug it into the wall, you recharge it back, use the charge, recharge it back, use the charge, recharge it back. Why eventually does your phone battery die? I don't know if you're raising your hand. Sometimes you raise your hand and I don't know if you're raising your hand or not. Because everything dies. So that's the morbid way of looking at it. So, short answer, every time this reaction happens, it's not going to completion both ways. You're also losing energy to what source? The wall, or I'm thinking of entropy, right? You have entropy that's happening. You're losing energy. Every time you do this, you're losing energy to the wire, to the universe. So there's friction between the electrons and the wire. So, guys, eventually your battery dies. So when you get to advanced chemistry in college, or if you do engineering, you'll learn like, okay, how long will the reactions last? You know, if you go 99.99% back each time, after a number of chargings, now you're at 99%, then you're at 90%. Eventually, you're not going to be able to fully recharge. So there's also contaminants. Like if you have something that's not zinc here, then you can get more contamination and the reaction doesn't happen as well. So here's your connection. Connect E naught being positive to a favorable reaction. E naught being negative is unfavorable. We can take unfavorable reactions and make them happen by applying energy. Yeah, Jonah and then Liz. There is, the question was, well, there's also like anions in here to make it electrically neutral. We just don't show them because they're not important. They're spectators. So the question is, where would you apply the voltage to get it to move backwards? In this case, I'm not that sure. Like how, like you'd apply. So it has to do with the current being flipped backwards. You would apply like one electrode here and another electrode here. So you'd be pushing electrons this way. So the current would be pushed this way. You'd push current in this way, which would cause electrons to flow back the other way. Don't worry about the semantics. Worry about this. Because Benjamin Franklin, really. Makes it confusing. The reaction going backwards does not want to happen. You are giving it the energy by applying electricity to both ends to force it to go backwards. Right? So you know how, like, think of freshman physics. You measured the voltage using voltmeters, where you clipped the voltmeters to two different things. You can push power through that way too by just like clipping, I forget what they're called. We just call them electrodes to both sides. I'll show you a better example, or the lecture will show you a better example on when I do it on Monday in F-Block. Yeah. Mm-hmm. So now you're talking about semiconductors, right? It's just different. It's just different. That is purpose. The question was about semiconductors. That is purposely adding a contaminant to allow electrons to move selectively. Right. Here you'd be adding a contaminant that would make it not move. That does not have bearing on this. Right. Okay. I'm going to ask you, we have 2 minutes left. Find the E naught for this reaction. So it's a little tricky. So assuming, here's the key point. So you're looking for something that has some H pluses. Look on your sheet for what this could possibly be. Okay, so guys, I wrote up on the board what the reactions are. You had to find O2, which is somewhere on your list. And I told you, I said it was acidic, so the H pluses plus the 2 E minuses make H2. Remember, early on, I told you that this reaction has an E naught of 0. That's just what we define as our arbitrary 0 point. This reaction you had to flip the other way, because it was oxidized instead of reduced. So we started with water, we ended with O2 and our acid and some extra electrons. So is this reaction thermodynamically favorable? No, that's what you need to be able to, yes?
But isn't it not an arbitrary scale? Because that's like
but it's all in comparison, right? Our E naughts are not really E naughts, they're delta E naughts. They're the difference between two. So it's arbitrary to do a single one.
But can't you solve for E naught from other things?
You might be able to solve for E naught for other things. Okay, so